Hello everybody, welcome to the aoe2 AI scripting tutorial number 7. This video we will have a quick recap on the programming levels, have a look what the computer player strategy builder guide is for level 1 to 3 programming, and the main part of this video is about using Boolean operators on facts. Boolean operators are not and or, NAND, XOR, NOR and XNOR. Recap programming levels. Level 1, basic programming level, which we have been using extensively until now. Level 2, strategy and personality level. We haven't really gone into this yet, but we have used it on occasion. Level 3, parameter level with strategic numbers. We have encountered this quite a few times already. Level 4, advanced programming levels, which is user patch commands or up commands. We have used it here and there. And level 5, micro level, the direct unit control level. We haven't used any of this yet. The computer player strategy builder guide. If you watch the first 6 tutorial videos, your knowledge should be high enough to start using some aspects of this document. This is a basic document usually delivered within an aoe2 folder. If you can't find it, see link 6 in the description. It covers a big part, but not all, of levels 1 to 3 programming. It describes facts, actions, examples, tips, and so on. For the level 3 programming with strategic numbers, it contains most of these numbers, but not all, and it also has a list of the defaults. It is a good starting reference for learning to program the aoe2 AIs. Don't get overwhelmed though with all the information. Write down the ideas you want to experiment with. Read the descriptions very carefully and think first what the subtle differences are or meanings are. And experiment a lot, because this is the fun part. Here you see the link to the Computer Player Strategy Builder Guide AI Expert Documentation. If you have a quick look at the table of contents, it gives an introduction describing different aspects of the programming. It has a facts list, an action list, parameters, and strategic numbers. Some examples, for instance, how to trade and so on. You can have a look at this by next video. Think about things, try things out, test things, and so forth. Don't get frustrated if something doesn't work. Keep watching these step-by-step tutorial videos. Put in debug chats to test when facts are triggered. Look for examples in the code of other AIs. Check strategic numbers and dev consts. Not all bugs are because you made a scripting mistake. There are quite a number of known and unknown inherent bugs in aoe2 AI scripting. Ask the community for advice. Also, you can email me at interlepus@yahoo.com. Now, for the main part of this video, we were going to talk about Boolean operators. The most used Boolean operators are not, and, or, and these three must be known if you want to do basic programming or scripting. The less known, less used, or even unknown Boolean operators are NOR, XOR, XNOR, and NAND. These are optional or for pros and experts scripters. We will create a fun experiment to explore all of their functions. I will visually describe the facts in different ways. I will also describe the Boolean operators in different ways in case one method is easier to understand than another. We are going to deviate slightly from the core purpose of aoe2 programming for this experiment. It might come over slightly odd or confusing, and if too difficult, skip this video and come back at a later date. First, to initialize, we want to comment out the chat in our tutorial AI or make a new AI. So we see here chatting data. We will select all of this, right click, block comment, and with the scouting we will comment out the chats. Save, and just to test, I want to see that there's no extra chatting to us, which is good. Counting. We want the AI to count. We will be counting natural numbers. Natural numbers for the mathematicians, so 0, 1, 2, 3, 4, 5 to infinity, represented with this n. It doesn't matter in this experiment if a number is counted twice. We could program that it counts each number once, but this would add even more level 4 programming, so just ignore the double counting for now. We will use the game time seconds for the counting, as game time in seconds has a one-on-one relation with the natural numbers. This is a visualization of natural numbers. You can have a person counting 0, 1, 2, 3, 4, 5 to infinity. You can have a line segment with points on the line 0, 1, 2, 3, 4, 5 also to infinity, or a Venn diagram with all the numbers contained in it with the name of the natural numbers collection. We want to create two subgroups of numbers. Visualize this can be two people each counting specific sets of numbers, like person A counts from 5 to 15, which is 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Person B counts from 10 to 20, which is 10, 11 up to 20. We can put these numbers into sub-Venn diagrams, A and B. You see some are communal, some are outside, all within the natural number Venn diagram. We can create two extra line segments, A and B. These are different representations of the subgroups of numbers we want to create. There are four possible input combinations corresponding to the four distinct areas in the Venn diagram. We see four areas. Mathematicians know that there are 16 possible outcome combinations or output combinations. We see that A can be either true or false, and B can either be true or false. More on this in a moment. So, how do we set up the counter for our fun experiment? For this experiment, we need some level 2 and 4 programming. Don't stress about this programming, as we will deal with the explanation in detail in a future video. What we want is we want the AI to count according to the seconds of game time. So first we declare a constant GL counter 1. GL counter is actually a goal, and it's our first goal, that's why it gets the number 1. We make a def const game time nil. Game time is a fact, and as we have seen, for instance, with research IDs and object IDs, all IDs get a constant allocated to them which is predefined, and I know that game time is predefined as nil. We will deal with fact IDs in a future video. We will make a def rule. Here we have to put something. I put X's there for the moment. What do we want it to do? We need up get facts, which means we are fetching a fact. What fact are we fetching? We want to have the game time, which is given in seconds. Game time doesn't have a parameter of its own. That's why you put a 0 there. And we want the seconds to be put into the goal GL counter. So the goal GL counter here, in this specific case, works as a variable. Then, as we used before, we want upchat data to player to who myself. And what do we want to chat? We want to chat the time, %d, and instead of that it's a strategic number or constant that we want in the D, this time we put the prefix for a goal, because we want to read the game time in seconds. Don't forget to close the brackets. I have explained slightly these commands, but the most important bit is that we are programming the AI to count. The fact section is what we'll be concentrating on. The actions in this experiment stay the same throughout the whole experiment as we are concentrating on the facts. First, we will start with the logical tautology. This is combination number 1. It's also the easiest combination, that's why we start with it. A logical tautology, from the Greek word tautologia, is a formula or assertion that is true in every possible interpretation. In layman's terms, we want it to count all the numbers. It's a good starting point. Whatever the line segments A and B are, we want the output to be true in all cases. We want it to count all the numbers. And how do we do this? What fact do we need that it would count in whatever case you would have? Well, we have already done this in our tutorial AI with "Hi, my name is tutorial AI. What fact do we use? True." So this is what we will start with, true, and true is true in all the cases. That's why it's called a tautology. We will save this and we will see that it actually starts counting. And we see here the time counting. As I said, that you see a number once or twice does not matter. You see that the script is re-executed once or twice every second, but the counter is counting according to the game time in seconds. So that works, and indeed we get all the numbers. Combination 1. With the fact true. Next we will have the logical contradiction, which is the second combination. In terms of logical operations, a contradiction is a case in which the outcome is always false. We also already have used this here, hi, my name is Barbarian, false. We don't want any numbers explained in layman terms. This is a representation. Instead of that we have all the numbers in the Venn diagram, we don't have any. The output is false. So we put false, we save, and we restart. And as you can see, it's not counting at all. We wait up to 25 seconds or so, and it still isn't counting whatsoever. We use the fact false. Now we want the third combination, which is marked here. We want it to count line segment A. This is a logical identity A. In philosophy, identity, from Latin identitas, is a relation each thing bears only to itself. Now we have to make A. How do we do that? Well, we use game time to count in seconds, we know all that. And on the one hand, we have the fact game time is greater and equal to 5. We will program this. Game time is greater and equal to 5. If we save this and we restart, we can see its effect. It will start from 5 and go up to infinity. A is smaller or equal to 15. So if we just comment that one out and put in game time smaller and equal to 15, we will see what we will have. And it starts counting up to 15, and then it will stop. It doesn't count anymore. Now, to get the line segment exactly, we need, of course, game time greater and equal to 15, game time smaller and equal to 15. This is what we have to define A. We will restart the video, see what happens, and it starts counting from 5 and it stops at 15. Exactly what we want. We have defined line segment A. Excellent. Now for B, we have to do the same. Setting up B. B is greater and equal to 10 or smaller and equal to 20. So we put line segment A there and we comment this out. Game time greater than equal to 10. Game time smaller and equal to 20. Save. We can comment that as B and comment that as A. So A is deactivated. If everything is programmed well, it should count from 10 up to 20. We're waiting, and indeed it starts counting from 10 and it stops at 20. Therefore, we have programmed the next combination, combination 4, which is this area the B line segment in the Venn diagram. As with A, we can see when A is true, we wanted the output for A to be true. The same goes for B. When B is true, we want the output where B is true to be true. And this is what we programmed. Before we go further, we will redefine A and B using the logical AND. This is what we have now. Both facts have to be true to form line segment A. The game time has to be larger or equal to 5, and game time has to be smaller or equal to 15. If all facts have to be true, everything is AND, then this Boolean operator doesn't have to be used like we have seen in the past. But we will implement it for A and B because we will need it in a minute. The logical operator syntax AND requires exactly 2 conditional groups. So the syntax of AND, open the bracket AND, needs 2 conditional groups. The logical operator AND is an element, so as all elements it needs opening and closing brackets. A small heads up, all logical operators require exactly 2 conditional groups except for the not logical operator, which only needs 1. So we can put this AND around A and an AND around B. We will just comment both out at the moment to see what we need. And this is what we did. We always have to check with all logical operators except for the not that it has 2 conditional groups. A conditional group, this can be rewritten like this because spaces and lines don't matter in the scripting language, and by using AND here between the red brackets, we have created a new conditional group. This is again a new conditional group. The same for B, and conditional group. Between the green brackets again is a new conditional group. Important. A conditional group is either a single fact or facts grouped by Boolean operators. What's happened here? Might seem a bit abstract now, but it will become more clearer throughout the video. Fifth combination we are looking for is the logical negation of A. A logical negation is an operation on one logical value, typically the value of the proposition, that produces a value of true when its operand is false and a value of false when its operand is true. In layman's terms, we want everything except A. You see, the white here is A, but we don't want A. We want everything except for A. So that means when A is true, the output has to be false, and when A is false, the output has to be true. And how do we program this? Using the logical operator NOT. Now, as I said before, the NOT logical operator is the Boolean operator which requires exactly 1 conditional group instead of 2. The NOT operator is also called the inverter or the opposite. A beginner's mistake, which is a syntax error, is to write it like this. We not game time greater and equals to 5, game time smaller and equal to 15. This is line segment A. This is a syntax error. It will not work. Say if we would make the syntax error not game time greater than equal to 5, game time smaller than or equal to 15. This is line A, and we want to inverted or opposite of line A. We might think to program it like this. If we restart the programming, it gives us an error. Why? Because the not Boolean operator, as stated, requires exactly one conditional group. Another mistake that can be made with the not is a logical reasoning fault. If you can't do this according to the syntax, not and then the two facts, some might think, well, then I can just not each individual fact. But actually, if you analyze this, what happens? Not game time is greater or equal to 5 means that it's equal to everything smaller than 5, meaning 0, 1, 2, 3, 4. Not game time smaller and equal to 15 means that it's equal to everything that's greater than 15, meaning 16, 17, 18, 19. Seeing that these two facts need to be true, we get a result of the combination of these two facts of nothing, because nothing is common in these two facts. In other words, when one fact is true, the other one will be false. When the other fact is true, the first fact will be false. There is no overlap, so it will count nothing. And this is where the AND comes in handy for the first time. The AND makes of the line segment A one conditional group. So we put in not like this. We see that not has one conditional group. This is a conditional group because this AND operator groups these two facts. I hope this is clear. Not A is not and these two facts. Will we get everything except A, programming it like this? We shall see. It counts up to 4. And it starts again from 16 to infinity. This is exactly what we wanted. We wanted to count it up to 4. We wanted to include the bit of line segment B that's not in common with A, and from 21 onwards too. So we have found the logical negation of A with this not Boolean operator. Now we are looking for the logical negation of B. So we just comment that, and for quickness we put not, and don't forget the bracket at the end. This is why Notepad++ is handy. You can see what brackets belong to each other because they're marked as red. That bracket is for this group, and so on. Anyway, we have not B, which means we have negated B. Save. So we want everything, as you can see on this picture, we want everything except for B. We will see if we have programmed this correctly. It starts counting up to 9, and then it continues from 21 onwards, which is what we wanted. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then B starts, and then from 21 onwards, which is the negation of line segment B. This was combination 6, not B. Logical denial, combination 7. We want A, but without B, meaning we want everything of A except if it belongs to B. So instead of that, we want the whole of A, we want the whole of A minus the bit that belongs to B. How do we program this? We want A and not B. Let's see what the result is. We want 5, 6, 7, 8, 9 if we have programmed this correctly. 5, 6, 7, 8, 9. And that's it. Very good. We've got the logical denial A without B. Now we want B but without A. So we put in not A and delete the not of B. We save it. What do we want? This bit of the Venn diagram, which means numbers 16 to 20. So everything of B except if it belongs to A. Let's see if we have programmed that correctly. (16, 17, 18, 19 and 20), and it stops again. This is again what we wanted from 16 to 20. Logical denial. With the absence, the omission or avoidance of, not with no or no one, lacking, free from, excluding, and so on. Now we want the logical conjunction 9. Instead of that it gives what we need to program, it will now give us the operator, and we have to mentally guess what the outcome will be. What will be the outcome of AND A and B? So we've got line A and B here, and now we start playing with the logical operators, and we've got a bracket here too many thanks to the script. We can see, yeah, that is correct. So what will the result be? Let's have a look. (10, 11, 12, 13, 14, 15). So it counted from 10 to 15. That's this part in the middle. If we weren't thinking and we would have thought and A and B, you might think it would give both line segments A and B. But in logical conjunction, it's what both is what A and B have in common. This is combination number 9. Logical disjunction, combination number 10. We see what OR does. So we change the AND into OR. Mentally think, which numbers will it give us? 5, all the way up to 20, and then it stops. It gives everything of A and B together, which is this section. It counted from 5 to 20. Anything that's either A or B. This is the table. If either A or B or both is true, the output will be true. Combination 11. Now we come to the expert Boolean operators. NOR. What do you think the outcome of NOR will be? It starts counting right away from 0 to 4. And then from 21 up to infinity. So it counted everything that's neither A nor B. So outside the A and B, it counted up to 4, and then 21, 25 onwards. Combination number 12. XOR, the logical exclusive disjunction. After the logical joint denial, the names are getting more fancy. But what does the XOR do? XOR A, B. Let's test this out. Five, 6, 7, 8, 9, 16, 17, 18, 19, 20. So what did it do? It counted everything that's either A or B, but which is exclusive to A or B. That means we have to look at A and B, but not what they have in common. So that is left out. It counted from 5 to 9, and then from 16 to 20. Very interesting. Combination number 13. Logical biconditional, XNOR. What will this experiment give as a result? Starts counting from 0 to 4, and then from 10 to 15. And then from 21 to infinity. Interesting. So, which combination did it make? It counted everything that's not A or B, and what A and B have in common. So when A and B are false, the output is true. When A and B are true, the output is true. If one of either A or B is true or false, the output is false. These thingies are interesting to study, to see patterns. Like with the XOR, you see if both are the same, it gives false. When both are different, it's true. And here is the opposite. When both are the same, false, false, it's true. When both are true, it's true. When both are different, it's false. On to the next. Logical denial of conjunction, NAND. Combination number 14. Let's see what this will give. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 16, 17, 18, 19, 20, 21, 22, up to infinity. So what does it give? Everything except what A and B have in common. Meaning if both are true, the output is false. Combination 15, logical implication. We want everything except what's exclusive to A. So how do we program that? I could peek, but I don't want to. I want to think about it. If we have not, we have A and not B. We only have this, but we want not like this. I'll go and peek. Not and A not B. The opposite of that, yes. So what should we have? Everything except 5, 6, 7, 8, 9. Five, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And so on. Yes. Of course, as you would expect, the last combination is everything except what's exclusive to B. So we move this not up to A. We save. We want everything except 16 to 20. It stops at 15, very good, and it continues from 21 onwards. Now we've had the 16 combinations of the possible outputs. To end, I have made one mistake. In the Venn diagram here, I forgot the 0. The 0 is also part of the natural numbers. With 3 facts, there will be 8 possible different input combinations and 64 possible output combinations. It gets tricky very fast. Well, 64 of these. Tip: keep the facts as simple as possible. Only use complex Boolean combinations if you have a good understanding and visualization method of the possible results. This is an example of a Venn diagram with 6 facts. It looks pretty, but very confusing also. Combinations are possible if we stick to the syntax rules of 2 conditional groups for each Boolean operator, except for not, which has exactly 1 conditional group. Tip: write the brackets so you can distinguish the different elements clearly, or use your scripter to detect which opening and closing brackets belong to each other. Remember, using the logical operator NOT, what the solution was when we had two facts or conditional groups, we use AND. What if we have three conditional groups? First, we have to group it like this, AND, which is conditional group 1, and start a second AND here. So this AND has two conditional groups, this AND also has two conditional groups, and then you can put the NOT, which has one conditional group, this AND here, which groups all the rest. What if we have four conditional groups? We can use the AND here, conditional group 1, and open another AND, conditional group 2, and then open another AND for conditional group 3 and 4. It can also be rewritten like this, it doesn't matter in this case, as long as these Boolean operators have two conditional groups. What's the opposite then of four conditional groups? The NOT, which has one arrow pointing to one conditional group, or in this case like this. This is a combination fact example that I found in a Barbarian code. You see this OR has two conditional groups. The second conditional group AND has another two. This OR goes to this AND, which has these two, and this OR over here. This is all syntax correctly done, because each Boolean operator contains two conditional groups within it. This is a combination fact example from ProMe. Again, this OR points to two conditional groups here, another OR to here, this OR goes to an AND, which has two groups, to another AND, this AND goes to here, which is then an OR to there. Copyright disclaimers. These Venn diagrams images that I have used in this presentation comes from this website. I was also inspired by this internet website which explains the different gates AND, OR, XOR, NOT, NAND, NOR and XNOR. And I discovered personally that there were other Boolean operators than AND or NOT by studying Barbarian and ProMe AIs. Thank you for watching. Don't forget to subscribe to see future videos to get notified, and see you again. Hopefully it was very clear. Otherwise, feel free to ask questions and email me. Thank you. Bye.